Welcome to Rubber Duck Engineering. Tonight, we are going to build a Linux process from scratch. Amazing.
Scratch.
Well,
Well,
mostly
not
from
just
scratch.
from scratch. Important distinction, because I originally thought when you proposed this that we were going to be typing in assembly, but it turns out we're going to be typing in C.
No, we're going to type it in the assembly of the common folk, C. But we're not going to use libc. There's going to be no standard library. All the code that does anything is going to be code that we type in.
So we have to use our stone knives and bearskins to talk to the kernel ourselves?
That's right. There's an amazing kernel underneath us that can all singing, all dancing, all amazing, and we're gonna poke it with a stick and see if we can get it to dance. Dance, kernel, dance. Do something.
Cool. Shall we hit the code machine?
Yeah, let's do it. We started the code machine.
We did. We started in the code machine, and then I realized we mostly just had a giant green screen and tiny faces.
I mean, green screens are beautiful. All right, so here we are. So I'm running in a VM special for this purpose, just so we don't break anything with our stick. And
so this is like Docker running on your machine or something?
Yeah, I just built the VM using this very, very simple Docker file just to have a very clear understanding of what's going on. And then this is our program, at least to start with. Okay. So notice that we don't have a main. Main is a dream that libc had one day. So if you don't have libc, main doesn't mean anything. So the thing that actually means something at the lower level is underbar start. So if you, we can just actually start from the very beginning if we want.
So underbar start is a magical symbol name that appears in your, because you start with an elf file. I'm gonna try and recall my assembly knowledge, and you can tell me what works and what's right and what's not.
Yeah.
So you start with an elf file that's split into sections.
Correct.
And there's some magically named sections that start with dot.
Mm-hmm.
And I think it's dot init is the one that you kick off. And then there's also a symbol table. No.
Yeah. So
help me.
So the way Linux works is the Linux kernel has knowledge of the ELF file format. So when you compile a program for Linux, you end up with this ELF file that has a bunch of stuff in it, like you're describing. And then Linux will load that into a process for you by interpreting some of the sections. Most of the sections it ignores, but some of the sections it knows. And so just to give an example, let's just try to compile this function. So I called the function banana. I'm going to try to build. It's going to tell me that it's mad, but it's only a warning.
Okay.
So it said,
so what it's saying is that when it loads this ELF file, it's just going to jump off at the 1000th offset and set the program counter to 1000 offset and just hope.
Correct. It's just going to, whatever's there, it's going to try to execute it. So if you go one level lower than we're going, when you actually link your program, you link a little stub that you put at whatever it is, the 1000th location, so the very beginning of your file, that just jumps to underbar start. And so underbar start is actually a concept from the toolchain. So the raw material that the toolchain gives you knows about underbar start. Linux just knows about the entry address that it jumps to. And so if you name your entry point, so we can actually run this program that we just made. It was just a warning.
Do you know why it's 1000? And I assume it's not 0 because 0 is in your process and 0 would be like null. Or is 1000 not your process?
Well, these are just offsets inside your, so it's going to map your code segment. This is an offset inside your code segment. I'm not sure why they don't do it from 0. Maybe there's a header they put there that I don't know.
Okay.
And now I built it with underbar start, and now it builds. Oh, we should just show what the build file does. So the build file is also incredibly simple. So basically, we say clang, and then this is the magic thing that you pass to clang. Let's say I don't want your C standard library. That's too refined for my taste. I want to bang rocks together.
Yeah.
And then feed it the C file, tell it the output, and I turn on a bunch of warnings and errors so we're not totally lost in the woods.
Okay.
There's more things you can disable here if you don't want the little stub that jumps to underbar start. You can also turn all that stuff off. But so now we have this program. If we run it, it crashes.
Mm-hmm. And you and I talked a little bit in the pre-show as to why that is.
Yeah. So what's happening is the program jumps to this location and starts executing, and ain't nobody told it to stop. So it just keeps executing until it reaches the end of the page that it was on, and then it page faults because it wanted to fetch the next instruction and there wasn't any more instruction.
You would think that it would crash before that.
So I think actually, if we go look at, if we dig in deeper, I think we'll find is, in addition to putting a little stub at the beginning of the program, I think they put a little stub at the end of the program that crashes in a controlled way.
Well, because otherwise you don't, like, what would you put for the rest of the page, right? So say they don't fill the full page because the page is like 4K of memory or something like that, right? I don't know what page size is on Linux these days, but like
4K, yeah.
What would you put for the rest of the page? Zeros? No ops? Like
probably zeros. I don't know if zero counts as a no op or not, but
I don't know what the no op instruction like value is in binary or hex. No op is just tells the CPU to just not do anything for a cycle.
Go to the next instruction.
Yeah.
So now, in order to make the program actually exit correctly, I'm calling the underbar exit syscall. And so I imported this header only library to just help make syscalls. So we can go take a look at that. It's not magic. It's actually very, very simple-minded. It just is makes it a little bit easier to do this stuff.
Yeah, I'd have a couple questions about this. I don't know.
Okay, before we go there, yeah.
Well, let's look at the library first. So this header is something I think you said you imported from the Chromium project.
Yeah, the Chromium project just provides this header. So this header is a little so it basically defines all of the structures you need to make syscalls, and then it knows all of the numbers for the syscalls. So when you trap into the kernel, if you wanted to issue a mutex weight, that's number 0. And if you wanted to issue these are them. Like
maybe we should cover what syscalls are. I don't know if all viewers will know what that.
Okay, syscalls are, so the kernel is in some other address space that you don't have access to. And so a syscall is like a function call into the kernel. But it's not literally a function call. Instead, what you do is you load up your registers in some way that the documentation tells you, and then you issue some instruction that tells the CPU to interrupt what you're doing and go ask the kernel to do something. And so on Intel architectures, I think it's like interrupt 80 is the one to do this. On ARM, I think there's just an instruction called sysenter or something that says, now go talk to the kernel. And so by convention, the thing you load up into one of the registers is like an index into the syscall table. And that says, hey, kernel, what operation did I want you to provide?
There's actually probably a couple more things we may, it depends on who's watching. Like we may need to explain, like, we could talk about like, what is a kernel? That calling convention that you describe, I think, is actually relatively normal. You tell the computer later do something, and then it has a magical location that it knows to look for the information, similar to how we did the process start, right? You said to the computer, hey, start this thing, and then it knows, oh, the magical location where we go actually find the code to run is at offset 1000 in the binary. Do you want to explain what a kernel is?
What is a kernel? That's a good question. So a computer at some level has a bunch of hardware that's attached to your CPU. And most of the time when you're running a program, you don't want to have direct access to that hardware because the hardware doesn't know the rules of the road. So it doesn't know, like, my web browser should have access to this kind of hardware, but my text editor shouldn't have access to my microphone or things like that. So you need something to figure out, like, how are we going to share all these hardware resources between these different programs? And so the kernel ends up being a special mode that the CPU executes in that has access to all of the hardware, and whose job it is to let the other programs running on the computer share that access, and then also gets involved in limiting it for security and saying only these things can access these pieces of hardware. And so the way this ends up working is when your process is running, you have like half the address space. So the like addresses from 0 to like 2 to the 31 are like those belong to you, and your program can do with them as you wish. And the upper half of the address space from like 2 to the 31 to 2 to the 32 on a 32-bit machine, that's memory your program doesn't have access to, but the kernel does. And so when you do this, I want to enter the kernel mode, the supervisor bit gets flipped on the kernel, on the CPU. It says, okay, now you can talk to the hardware. Good job. And also the rules for accessing memory get changed so that now the high memory or the upper part of the address space becomes readable and writable. And then there's some entry point in the kernel that the CPU jumps to.
Yeah. So correct me if I'm wrong, but like my mental model of the kernel is that it is not maybe the lowest level of software these days, but it's pretty far down on the software stack. And its job, as you said, is to talk to the hardware and often protect the hardware. Mm-hmm. Like it's the thing that knows how to turn on the fan when the thing is overheating, right? It's the thing that knows how to, throttle up and down the CPU. It does all that very low-level hardware stuff so that things on top of it can, as you talked about for security reasons, either not have access to certain hardware, also partition between different processes, like the kernels provide an idea of a process. So like you can have a web browser running separate from a notepad, and like the two cannot access each other's memory.
Yeah, that's exactly right. Like when you write a kernel, you have to be very, very careful because like the safeties are off. Like if you tell the computer to go really hard and don't pay attention to its thermal feedback, it will melt. It will catch on fire and burn.
Yep.
If you turn on the some I/O peripheral and you tell it to please dump its data at this location, it'll just dump its data at that location and destroy whatever is there. So, yep. But you need that in order to actually make the hardware do anything.
And so then to go back to the file that you have here, so the way you talk to the kernel is that you tell the hardware to interrupt you, and you write in the special location, hey, I want syscall, which is basically function call in the kernel, number 271, or whatever the heck the number is for the syscall that you want. And then, by the way, the data, the arguments for all that syscall are splatted out somewhere. And this file both puts names to that data, or both put names to those syscalls, so they're not just numbers, as well as has all the structures, the C structures. So you have a chance of splatting out the arguments and the return values from the kernel, reading them to and from in C. Is that correct?
Exactly. So we could write all this ourselves. Like obviously this is just a 6,000 line file somebody wrote, but the critical line in this file is this one, which says trigger and interrupt. So it's this interrupt what we're doing. And this is interrupt number 80, which I guess is like switch to kernel mode, please. And then the other interesting thing this does is, you can find an example of this. On the way back, so the kernel is going to go do its work, and then it's going to return control to us. And the way Linux works, it returns its value in a register. So it has a bunch of side effects, and it gives you back one register's worth of data. And so like if you, what's a good example of a thing? If you call open, the open syscall, it returns you an integer, which is the file descriptor that you opened. But it can also return you an error. And so usually in C, what happens is you go find the error in a special variable called errno, as opposed to having it come out the return value. But the way syscalls actually work is those error numbers or error codes actually get sent through the return value. And so when you return from a syscall, there's this little trampoline in user space that basically checks to see if the return value is negative. And if it's negative, then it shoves it in this errno variable and then changes the return value to -1. And otherwise, it just returns the value that the kernel returned. And so that's why.
Okay, so if we go ahead, sir.
Go ahead.
I was just saying, so if we go back to your main.c, that's why we have to provide this, that error location is just some macro in this header to say, hey, where do you want us to store this error? This has nothing to do with the compiler. This is the header.
Okay, so now, right, correct. This is nothing to do with the compiler. This is purely the header being interested in this. But the reason the header has picked this structure is because this is the conventional structure on Linux. So like glibc, and it's not required. Like your libc can do whatever it wants to escrow errno for you. But this is the common one that people do, which is there's some symbol that libc exports. That is this function that says, give me the address where I'm supposed to put my error node.
Oh, interesting. Why would libc export the symbol as opposed to just handling that all internally? Do you know?
Excellent question. Yes. So, like many things, this was designed a long, long time ago, and it was designed before threads were a thing. And so one of the like no one uses this way of returning errors anymore because it doesn't work well with threading. Like let's suppose two threads are calling syscalls.
Yeah.
They could stomp on each other's errno. So what happens is this errno location actually is thread specific. And so the real implementation of this in a real libc would go look in its thread specific data structures and give you a different errno location for each thread. Here I haven't done that because we're doing simple things. So I just have, so if I were to spawn multiple threads here, they would go clobber their errnos. And
we're not even using libc.
Correct.
And again, our viewers probably know all this, but threads are, again, ways of having separate streams of execution within your process itself. But threads in C, at least, don't have any protections to not clobber on over each other. They can just read whatever memory they want and write whatever memory they want. In other higher level languages, threads or workers, say as they exist in browsers, for example, can't just stomp on another worker's memory. But in C, they can.
Yeah, so actually threads are a C language concept that's implemented by the C library, at least on Linux. And on Linux, the concept in the kernel is called a task. And when you create a task, you start with your current task and you clone it. And there's like a bit field of like, I don't know, a dozen different flags. It'd be like, what do you want to share after you've cloned this task? Do you want to share your address space? Do you want to share all of your signal handlers? Do you want to share your file descriptor table? Do you want to, anyway. And so when you create a thread, C library will pass a certain mask of these down, which basically says, share my address space, share my file descriptors, share my, mount table and stuff. And so then that's how it ends up with different tasks that are executing at the same time that all use the same address space.
Are tasks the same structure in the Linux kernel as processes? Are processes tasks as well?
Correct. And so a process is also an illusion created by actually nobody. It's not. It's I guess
we just call them processes, right? It's what the shell does.
We call them processes, right? So there's no so in C, like C11, there's a function called thread create, which says, okay, create me a thread. But there's no process create in libc. So when you processes are just even a higher level concept.
It's a task that is a parent. I presume it's defined as a task that is a child task of a init or something like that.
No. So it first of all, it has no definition, but like it's what we mean conventionally by a process is we've called the clone syscall. Whoa, all the chat messages showed up at once.
Yeah, StreamYard was kind of busted for a little while. I was wondering if anyone was even here. But it turns out they are. Hi, everybody.
Let me finish this thought, then we'll go chat. So it basically, you can think of a process as another convention of this bit mask that you pass. And so there is a concept in the Linux kernel called a task, a thread group, task group, something like that bundles up, that is magically arranged so that its boundaries correspond to this conventional use of the flags. Okay, let's see the chat. Hey, Frank, thanks for coming. Sorry the messages were queued up and we didn't respond right away.
Yeah, StreamYard was really, it wouldn't even tell us like if anyone was watching. And I was like, are we broadcast? Whatever. It was confused for a moment.
Hey, Andrew.
Hey, Andrew. and sticks.
Ah.
Mr. Barth, it's Dr. Barth, but yes. Mr. Barth is very good at coming up with good ways to explain things on demand. Very impressive, yes.
I've been digging through this stuff for a while to try to understand it.
Yeah, so we were talking about.
Yeah, so I think like an interesting thing we could try to do is we could try to create Hello World, right? That's sort of the first program you create. So I think Hello World should be pretty easy.
That's very kind of you, Johan.
Thanks, I appreciate that. So we can't call printf. So if you bust open your C book and they say, how do you write Hello World? They tell you to call printf, but we can't do that because printf is a C library function that has a whole bunch of formatting stuff. So instead, we need to make the write syscall. So we're going to call write, and then the first argument to write is file descriptor. So we're going to do file descriptor 1.
So does the kernel set up the standard 3 file descriptors of standard in, standard out, and standard error?
Excellent question. No. The kernel cares nothing about those things.
So who sets up those magical file descriptors?
Excellent question. So in most systems, so we're running Ubuntu here. So it's in Ubuntu, it's going to be a init. So init is the first process that gets run in user space. And so when init starts up, it actually, if you look in libc, it'll your like glibc, for example, will I'm not sure about glibc, but definitely Bionic will detect whether its PID is PID1, which is for init, and it will initialize its standard in and standard out differently for these things. But basically what init does is it creates, one of the jobs of init is to build the dev tree. So if we go just a little detour.
So to go over, so init is it the first program, or it's one of the first programs that run when you boot a machine?
It is the first one. First user.
It's the first one.
Yeah. There's a bunch of tasks inside the kernel that might predate init, but it's the one that's in user space. Yeah.
Okay. And it does a bunch of things, but one of them is that it's also the zygote process, or is that separate on Linux?
Yeah. So essentially to first approximation, every process running on your system was forked from init or transitively from one of those, or cloned. That's not actually true. It is possible for the kernel to autonomously create a process in user space, usually as a child of init, but it's very rare. That's not a.
But it would also break a bunch of conventions. Like that specific program would not have standard in, standard out set up for them, because when you fork, which is you copy the process, and then in the same way that you talked about this task spawn, right? When you spawn or clone or whatever the syscall is in Linux, it copies everything. And it can copy everything, including some portions of memory, including some file descriptors, for example. And so it gets itself into a mode where when it spawns you, when it copies itself to you, 0, 1, and 2 are set up to standard in, standard out, and standard error, correct?
Right. And what does that mean? That means they do something, like they go to the system log, or they what does it mean to print it? It's got to go somewhere. So right now so this is running inside a Docker container. So we've attached the standard in and standard out for this shell back to this terminal. Right.
And that was another communication that went to init, or like who
how did Docker spawn this shell? Good question. I don't know.
Or just how does the shell even get to say, no, I want standard in to be this?
So it'll create PTY, which is a pseudo terminal. So there's a if you look in dev PTS, you can actually just see it there. It's PTMux.
Well, like I know that when you're mussing around and you're running C or whatever, you can just set your standard in. You can change.
Yeah, it's just a file descriptor. You can close it. You can put a new one there. Do whatever you want.
Yeah.
But it's telling you what the shell actually does. So what the shell actually does is it goes and opens this thing called PTMux.
Okay.
Which creates a new pseudo terminal, and the pseudo terminal is a very handy thing that
is this buffers, I assume?
Yeah, it's like a little buffer inside the kernel that understands things like line editing, and it understands like window resizing, and like has a bunch of things related to terminals. And so then the
I'm glad my kernel has code related to terminals in it.
well, you might see why there's a motivation to create a new kernel, but the the shell holds on to what's called the control end of the pseudo terminal, and then gives the child end of the pseudo terminal to the program that it runs. And then those programs can fork and etc. And they'll hold on to the child end. And then the shell can do things like suspend all programs attached to the pseudo terminal. And anyway, I don't want to get into pseudo terminal.
Yeah, we're off in the weeds a little bit, but it's interesting to me. So my first job in Silicon Valley was working at Apple as an intern on the BSD technologies team.
Uh-huh.
And I did not know much about low-level BSD, but I learned a lot that summer from people who did. And we're hearkening back to some of that knowledge, but you obviously have done a lot of this more recently than I.
But I have to like implement these. I have to. So my job right now, I'm implementing the other side of many of these contracts. And if you really want to understand how a thing works, you should implement it, and then you'll know in excruciating detail how to do this. Okay, so now we have to guess how many characters is this? That's not nearly enough.
Oh,
5,
no, it's
6,
5,
7, 8, 9, 10, 11, 12, 13. Is that right?
That sounds right to me. Do we even need we need the new line if we want, because the terminal is going to take. Is the new line required in this?
No. It'll just let's take the new line out and see what it does.
Do we need to flush when we write? Is there a sys flush?
No. So that buffering is done in well, there's different kinds of buffering. Sure, let's do sys flush.
I have no idea what sys flush even does.
I think it's f flush is what we need. So the regular flush without the f is a libc thing that flushes libc's internal buffers. F flush, okay, I think will flush the actual
file descriptor buffers.
Yeah. Let's try it without that first, just for entertainment's sake.
Okay. I was expecting this to just right over the top of your terminal, but not send. Yeah, right. See, it didn't. Yeah. So you can see how it appeared right before where your line should be. So that makes sense to me.
Well, let's put the new line in just for this thing.
Mm-hmm.
So it is.
And if we make it 14 instead of 13, I suspect we'll just have gunk. Maybe we'll have a seg fault.
That's a good question. Well, so exactly after 13 is a null byte, right? Because like strings in C are the characters then followed by a null. So the question is, what would be after the null? And the answer is whatever is in the constant table.
We're doing my learning style here, which is that like when I see a thing and I don't fully understand how it works, I just poke at it.
Yeah, that's the idea. Okay, so we did Hello World. So here's Hello World.
Let's see if I can break it.
You want to break it? What you want to try?
Yeah, well, let's see 14 or 15. I'm just curious. I know this is not what we set up to do in the show, but
no, it's cool. So 14 is going to be okay because we're still having defined behavior because we know that the next character is going to be null.
But it won't do a seg fault because we're not going to run off the end of the page.
Right. So let's see if we can hex stuff it. 0A. I don't see the null.
So the pipe there is redirecting standard out through hexdump.
Right. So we can actually see
hexdump is taking it as standard in.
Yeah, I didn't see the null, which made me sad. But let's make a bigger number.
Well, you could try 13 18. Just to see what hexdump says. But okay, that's fine.
Oh, you know it is here. This was the null right here.
That's 0, 0.
Yeah, it's just because it's little endian, right?
Okay.
That was
Slow down. What did I do?
You're breaking things. Hey, Adam.
Oh. That's our role. We got to break things.
Okay, so here we go.
So now we just have a...
So there's more nulls, and then there's something that's not null. Anyway, we're just so there's a segment inside of our elf binary that has our constants, and so we're just like going through that thing. And eventually we'll run off the end and probably seg fault or do something else.
Yeah, because if you go back to your main, So when you compiles hello world, what actually gets returned there is a string pointer into your constant table.
Correct.
It's a char star into your constant table, which is the table at the beginning of your binary or somewhere in your binary. What the compiler made for you of all the constants.
We can look at that using this tool called readelf. So readelf knows how to parse this ELF file format and tell you interesting things about it. Like it knows how to decode it. So it's telling us that this thing is a dynamic executable that's meant for System V Linux, System V Unix, of all things, and it's really meant to be run on an advanced micro device.
Is it really System 5 or was it System V? This predates me. I wasn't around for that.
Somewhere in here, it'll show us our string table. So here's all the stuff that we did.
Yeah, so this is like all of the assembly of our binary.
Yeah. So here's under our end, which I think is the thing that the compiler shows at the end to make sure that you crash.
This is not. Oh, this is the symbol table. Sorry, this is not the assembly. This is the symbol table.
Correct. We can get the assembly out of this if we want.
Yeah.
But the I don't know why our constant doesn't have a name.
Where is our constant?
Where is our constant? That's a good question.
And there's like objdump or something is a similar thing on Mac for Mach-O. Maybe I'm thinking of maybe objdump is the ELF one. I remember having to learn some of this because the Mach-O tools, which was Mac's wrapper around the executable, were always different. It was odump.
Anyways, there it is.
Yeah.
So after some enormous number of zeros, then it goes hello world, and then new line, then a bunch of zeros, and then that same garbage that we saw printed out on the console.
Yep.
It's all just sitting there.
So the C compiler sees that string, and it replaces it with a pointer. It gives you back a pointer, but it just gives it to that static table that it slammed in your binary somewhere.
Yep.
Okay, so we made hello world.
So should we try echo?
Sure.
Because echo is fascinating, right? So like if we think about it, when we're writing a normal C program and you get called in main, it gives you your command line arguments. But
start does not appear to have an argv or whatever.
Yeah, so where are they?
Where would they be? I presume they're the task when it's created probably has a name that's like a long string that includes the arguments, and somebody has to parse them out of that. So there's probably like a give me my task name syscall.
That would be very sensible, but is not actually how it works.
Oh, I don't know if it's sensible. I would, in a modern system, I'd parse them out for you. But
when I say sensible, I mean that's how Windows does it. So to the extent that Windows is sensible, it's sensible. No, so the way Linux does it is they're sitting on the stack.
Sitting on the stack. So somebody pushes that. Well, yeah.
So
but I thought the stack was a libc. No, it can't be.
Right. So when your process gets initialized, when Linux initializes your process, it spams out a bunch of stuff on your stack, then sends your stack pointer to right above that, and then jumps to your binary. And so the very early thing that libc does in its entry is go parse that data by walking backwards from the stack pointer.
Does it have like markers between the?
Nope.
Like how do you know? Because it's variable length, for example. The command line args are.
So argv has a bunch of addresses, and then it has a null address, and that's the end of argv. And then there's environ, the environment block, same thing, and then it ends with I think 2 nulls, and then there's your aux vector, and then that ends with 2 nulls, and there's some alignment rules, and then your actual strings that are passed in argv are then just sitting there below the aux vector. But we'll go find it. Let's go find it.
This is all. It just reminds me of the statement. I mean, this was all when it was not a billion operations a second from your computer. Things ran at 60 hertz or whatever. But this still reminds me of the premature optimization is the root of all evil. and probably email.
Well, this stuff was all designed back on like the PDP-11 or like, you know, I don't know when exactly Linux, where this like argument passing convention came from.
So if we print our stack pointer, which I'm not even sure how you would do that.
You want to print the stack pointer?
I guess a way I could print the stack pointer, it must be some, how do I get my stack pointer in C? You're trying to, I mean, you could make a stack variable and then get the address of that.
Yep.
Like, how are we going to even start crawling back down the stack?
I mean, the way libc does it is just reads the register. It just writes some assembly. It says read sp and dump it into a variable.
I see.
But
okay.
Let's put our time spec here. So our.
So why are we nano sleeping?
Oh, what I want to do is I just want to have the program go to sleep, and then I want to go look at its memory maps.
Oh, okay, sure.
Proc. I just don't want to exit.
Okay. And why do you need a time spec? Oh, because that's the nano sleep convention?
Yeah, I don't know. Is there a better sleep that I should use?
You, I'm sure, know the syscalls of Linux much better than I do.
I don't actually.
Struct time spec. This is like old school struct.
I don't know. Maybe there's a better way to do this. I think this will work. I'm not sure. No TV spec.
Can you go back up?
Here.
What's this? Why are you defining struct? You're just defining a new struct time spec, and you aren't giving it any things in it.
Well, that's not what
in that line, are you not?
I want to do this. Is that better?
No, I think you want to just remove the struct from it. The struct keyword.
Oh, but
I suspect it's time spec T. But oh, I see. Those don't exist because those are.
Yeah, I don't think they define the time spec T.
So what does your header give you?
So that worked. Now I can't call nano sleep. Because I can call maybe usleep. Is usleep a syscall? Okay, here we go. Just call it usleep. That'll be easier. But sometimes it's hard to just even remember like which things are libc wrappers and which things are actually syscalls. No,
syslseek. Okay. I'm looking up Linux syscalls.
What is a sleep syscall?
I remember there's like man, and then like man has the different sections. Like 1 is for programs, and then 3 is for like libc calls, and then there was like 1. Is it like 7 is syscalls?
Yeah, something like that. It turns out to not. That's almost right until you actually go to figure out what is the actual binary convention. It's never quite right. No sleep.
So here's nano sleep. Struct time spec.
There's no sleep.
You could just have it while true. Like, why not?
Oh, that'll spin hot. Okay, we can spin hot. Why not?
Like, you got chords.
All right, we're gonna spin hot. Okay.
And then you're gonna daemonize it or whatever, and then kill it later.
Yeah.
Yeah, with the ampersand to daemonize it. Now you have your job number from the shell.
I actually want it's PID.
It's right there. It gave you both the job number 1 as well as the PID 9.
Let's go find. So this is our program now. This is what the kernel will tell us about our program. So like if we
well, this is the weirdness of Linux, where everything is a file, and so Linux is this virtual file system, which is your program's guts.
So yeah, so if I ls the CWD for this thing, This is the current working directory that program is running in.
Which is kind of cool and also kind of bonkers.
It's
the interface to walking around the guts of your program is ls and cat. It just like it represents. It's obviously a fake file system, right? But every time it gets a like, show me the directory of this call, it just like goes and reads whatever program structures and dumps them out for you.
Yeah.
It's
actually a symlink. So it's not the. You want to know the total craziest one? The total craziest one is proc self. So proc self.
When you read it, reads your own
PID.
Oh, yes.
So this is a thing. Normally in Linux, the file system doesn't matter who's looking at it, but this is a very magic symlink that has a different value depending on who's looking at it.
Yeah, I mean, it's cool. Don't get me wrong. And like, I get the idea of we already understand. We've taught the user. I don't think it was thought about this way, but like we have tools for navigating tree structures. CD and cat and ls and all that. Why don't we just use them to navigate the tree structures that are the data structures of our file or of our running process? But
so these are the file descriptors that we have open. So let's go look at our file descriptor 1. So this is our standard out for our process. You know about it anyway, but
so it's not the contents of. It's just the.
This is just like metadata about it. If you actually want to get file descriptor 1, it's here in the FD directory.
So FD info. These are all synthetic files.
Yeah, but if you were to open FD1, you would get a new. No. You would get in your process a file descriptor that you could then use to send output out the program. So we can actually do that. Let's try that. So let's echo banana into FD1.
And that's out or air? Out. One is out, right? Standard out.
One is out, yeah. So because we've daemonized our program, it came out FD1 of our program, and so we saw it in our shell.
Yeah, I agree, and I believe that it went that way, but it's a little harder to tell here.
It's a little harder to tell, but it did go that way. I promise you. Mm-hmm. Okay, but that was not the point. The point is I wanted to look at maps.
And you wondered if we could spend an hour talking about Linux.
So here are the memory maps inside of this process that we built. So we've got our executable mapped as read only at these addresses. We've got it mapped executable at these addresses. We've got it mapped read again here. We've got some read-write data mapped here. So this is the loader that we use to load our program, is also mapped in our memory. And then here's our stack, which is read-write. I'm not sure what vvar is. We can figure that out. And then this is another like ELF file that the kernel has injected that contains a bunch of code that we can run to help us talk to the kernel if we want, which is read execute. And then I'm not sure what the rest of the stuff is.
Is the DSO like dynamic? Is that something to do with dynamic linking or?
Yeah, so it's a virtual dynamic shared object. So this shared object or this shared library doesn't exist anywhere. It's a thing that the kernel has invented of its own accord and gets loaded into your process and contains a bunch of things that are helpful to you.
So the LD Linux, the loader, those were all injected by init, or those came from init when we forked from init? Like, how did we end up loading presume this is for dynamic linking or like?
Yeah, so we asked for this. So if we,
it's part of Clang. Clang gave us a dependency on that in our symbol table or whatever it's called there.
Yeah, remember I said we could drop more things out of our binary than just libc. We could drop out the linker as well with the loader.
Before the show, we talked about this. We our current binary is 14K, which is small, but not.
It gzips down to like 96K or something.
But the question is, could we even make it smaller? And you're saying we could by dropping because we've statically.
No, we dynamically like that. So if we go in here,
so
somewhere we should have our interp So if we go look at our interp will name that thing. Yeah, it says here we requested this program interpreter. So when Linux loads, when we ask Linux to load this executable, it literally doesn't literally load this executable. It loads this shared library and then tells this shared library to please load the executable. So some of the linking is actually happening in so like one thing this will do, it'll relocate our binary. So remember we had that string that was in our constant table. Our executable can be loaded at many different addresses, and in fact it's randomized for security, which means the actual address that string has is dependent on the loading. And so one of the responsibilities of this thing is to change the symbolic reference in our binary to actually fill in the actual address that is going to have. It's called relocating the binary.
Yeah.
So that's why this thing is mapped into our process, because we asked for it.
If we linked against other things, it would need to do things like the way that dynamic linking works, at least in my many years old memory of this, is that you have these symbols in your executable that are just stubs, and somebody at load time needs to map those symbols into actual addresses into the library that somebody else loaded into your process, mapped into your process, so that you can jump to those actual functions.
And so that's what this program does. And if we wanted to, we could write a thing that didn't have an interp that really started from nothing. But it's
okay.
Anyway, so
we were trying to crawl our stack to see where our arguments were.
Let's go look at that.
Where we last left our heroes.
So our stack is here. So our stack starts at this crazy address. So let's just copy that crazy address. And then
is it virtually? Does this get exposed to the file system? Like it has that virtual name?
No, these are just labels. They're not actually there.
Oh, okay.
But I don't know what that is.
Why not? ls stack.
Oh, permission denied. I don't actually know what stack is.
I don't know either. Okay.
But there is mem, which is what I wanted to go through.
And we should be able to read that as sudo.
Yeah, it's readable and writable by root. So let's go see. Let's go hex.mem.
Stack provides the symbolic trace of the function calls in the process's kernel stack. This file is provided only if the kernel was built with config stack trace configuration option. This is a 6-year-old answer on Stack Overflow.
Okay, it doesn't want me to...
I see, so it's for like stack traces.
Oh, it won't let me read the mem. But I'm root. Why won't it let me?
Did you...
Anyway, we could... let's go look at this a different way. So let's go back to source.
So do we need to write some assembly to load SP?
Yeah, let's write some assembly to load SP. That sounds like fun. So I'm going to kill this process now.
Okay. So we killed our hot spinning process.
Let's go load SP.
And then sys write it out. How to load SP via assembly?
I always have to look this stuff up. I can never remember.
Oh, well, this is... I was talking to one of my mentees this week and telling them that like half the job is just figuring out how to find this stuff on the internet.
ESP. ESP is what it's called on Intel. Just searching Google.
Print out the value of the stack pointer,
Yeah.
Oh, well, this is just doing it is just by using the first local.
Okay, we can do that
in
way.
Your function.
So we just declare a local like int.
It's just void pointer, right?
Void star
foo equals null, whatever, and then all you're doing is you're just grabbing the
address of foo.
You're grabbing the address of foo. You can initialize it to whatever you want, but
So that sounds good. So we think our stack is address of foo. So if we,
or it might be address of foo -4, but so it should be something like that.
Okay. Oh, I see. Okay, so we're gonna say like sp minus equals. We're 64-bit, so it's probably gonna be 8, right?
Right. We're guessing at this point.
So let's write out.
I also have no idea if the comments are working because I haven't seen any comments in a while.
Okay. So let's write out. Let's say 6 characters from here. How many words is bare metal? 5, 9. Let's see what this does. Because the first argument should be the name of the program. So we actually need this to be a U int.
MDR was kind enough to confirm that in fact the comments were working. Hello and welcome.
So we actually just need minus equal 1 because this is a pointer now. Okay, there's a pointer to a pointer, so we're going to move the pointer 1 pointer, which is 1, and then we're going to write.
We want to print it as like a hex or like an int or something, not as a char star.
Why not just?
Oh, you want it as a char star?
Yeah, because it should be the first argument to the function. Let's find out. I have no idea if this is going to work. It's going to be. An experiment.
To put it lightly.
That didn't look great.
Well, we can just keep crawling back. Why don't we just print -1, -2, -3, -4? Just see what happens. What's there?
I'm actually gonna make these smaller numbers so we don't go too crazy. Let's just print out, let's say 4 of them. Okay, so let's build on bare metal, banana, cake, float, args. That's garbage.
Okay. Just go back further. We have no idea what the structs look like here, right? Like there could be a whole bunch of stuff. Like.
It could also be plus equals. I never know whether the things go up or down.
Oh. It's true. I don't know which way.
I'll try going the other way.
I mean, you could test that theory by having a second. You could trivially test that theory by just having a bar, right? Put a second.
All right, here we go. GDB.
We're going to go look.
Does this work? What?
No. We are really doing it live now.
Doing it live. I did not prep this at all. It was a dream.
It seems like a reasonable question, though, is can you write echo? And the question is, can you get an argument without libc? And the answer is yes. It's not always straightforward.
I want to set a break on underbar start, right? Just so
2 bare metal, says Christopher.
2 bare metal. Banana, cake.
Yeah, for those who aren't familiar, GDB is the GNU debugger.
Yes.
He put a breakpoint B at underbar start, and now he's running the program with these arguments. That's what the run banana cake delicious.
Right, and then I did a backtrace, which shows you that there ain't nothing above you. You're really an underbar start.
Well, there's nothing recognizable, nothing you have symbols for.
And so let's see.
Can
I print out, what do I call it?
Dimitri.
SV? Dimitri, welcome.
You might need like, I don't know how you print register GDB. It's probably like $SP or something in GDB.
Maybe like Reg?
Info registers. Yeah, try. Yeah. $PC, $SP should tell you. Where you said it was ESP?
Yeah, ESP. Maybe it's RSP. This looks like an address.
RSP.
So this is our instruction pointer, right? RIP is definitely our instruction pointer. It's that underbar start. So here's our thing. So what is, so can I do like mem to go look at that memory?
I think you can just type print $. Oh, I see. You're trying to
Print the dollar sign.
It's been a long time since I've used GDB. No, sorry. The $sign was to use the symbolic register name in terms of getting what the
Kefmu. So somebody here must know how to print these things out.
You can all watch us flail.
Okay, there's got to be a way to have GDB dump memory. GDB dump memory. Yes. We have no idea what we're doing. Excellent.
Okay.
Dump memory.
GDB show memory at address.
Yeah, that's what I want.
I've totally done this a long time ago. X. Examine.
Of course.
X and then adder should show you.
Of course. 4. All right.
4 is not what you want.
That's argc.
Potentially. Could be.
Could be. That's the number of argcs. So what's next? +8. Will this work?
Are you sure it's plus, or does the stack grow up or grow down?
Oh, we're going to find out. Look nice. Null. And what's at 16? Oh, no, this is not looking good. 4? Not so good. So let's look at +8. +8 is that.
Do any of those look like characters? There's probably a way to do examine.
I want 64 bits. It's not giving me enough bits, right? This is like a 32 bits. GVX 64 bit. What up a 64 bit value?
64 bits is 8 bytes.
8 bytes, yeah.
Yeah. So you want X/G.
Of course. /G. Okay. This number looks.
I'm just reading the GNU, the GDB man page as we speak here.
Number looks no.
You can also get it to format it.
What if I do X? 8X XG stack pointer.
You can also add a number as to like how many of those. So you do X/1. You know, G would do like is what it's defaulting to. I see. You just did, yeah.
Back up 32.
You can also do this symbolically, right? You can do $SP minus 32. Or whatever it was. Did you say it was X?
RSP?
It may just be SP2. I don't know. It may map those two. Are we lost?
I think we're lost. We found our stack, but we can't find our arguments. Let's go look at Linux initial stack layout. Okay, local variables domain, save variables. All right, should we cheat and paste this code in?
Sure.
Okay, we're gonna cheat and paste.
Well, this uses standard I/O, but yeah.
That's okay. We'll figure it out. We look.
As in, you're gonna have to pull in libc to get this to work. I don't know what code you're looking at, but
I'm not gonna pull in libc. we're gonna do without libc.
Oh, I see. Because it had standard I/O for the printf, which we don't need.
So let's see. They did AX.
This is also for i386. If you're looking at the same thing I am.
Oh, it is. That's not so good.
Which it may be different for x64. This is why like people write these things for you, and we just sit on top of libc.
All right. Maybe Echo is ambitious.
I guess the thing that I would want people to take away from this is that this stuff is all knowable.
It is all knowable.
And it just requires a lot of digging. Stack frame layout. I don't want.
Yeah. So if you mess around enough in the memory here, you will find your arguments and you will find it in Byron. I'm a little sad that we couldn't demonstrate it, but it's there.
I'm looking. This is trying RSP plus 28.
RSP plus 28.
Can you print what RSP plus 28 is? I have no idea why that would be the right value, but
yeah, let me go back into GB.
This is a random 11-year-old Stack Overflow article.
Banana cake. Okay.
Yeah, here we go. This is someone trying to do exactly what we're doing.
Oh, great. Do you want to send me the link? Different. What do you want to print out? RSP plus 28?
Yeah, just try RSP plus 28. I'm not sure that that's going to help. Let's see. Essentially, the number of arguments that pass the program is stored in 0 RSP. The pointer stored at 8 RSP is a pointer to arg0 program name.
Every 11 years, someone tries to do this. Yes.
Okay, so this is the helpful article that I've found.
Okay.
And this is 11 years old, and I'm sure it has not changed. So there's a comment number 4.
Uh-huh.
Here I can post for those following along at home. Comment number 4. Mm-hmm. It's saying that I don't know the syntax of 0.
Yeah, this is 8 offset from RSP. So let's try this.
But what's interesting is that they're pointers, which I think we were expecting to see characters, right? They're pointers.
No, so we have to see a pointer, but I want to chase the pointer, right?
Yeah.
What did I do wrong? RSP plus 8. What did I do wrong? $.
I think you might want $.
So this pointer. So the question is, what is at this pointer?
Yeah.
Whoa. We did it.
A little Stack Overflow is all we needed. 3 minutes late.
What about 16?
Hold on. Well, what did you pass in run?
I passed.
But 16 is what it should have been. I don't understand this.
Why is it mad? Unable to display strings starting with G. Use B instead.
Well, so remember, plus 16 should be a pointer.
Watch hands. Yes. Okay, so let's try to do this in the code then. So we still need to get RS. We're not. Oops.
We kind of went over time here with our little adventure.
Okay,
but I think we're close.
I don't think we're that close, but.
Well, we don't even know how to get RSP reliably, right?
Correct. So we're just going to try this one time.
Are we going to just try and write our marker to see if that agrees with what RSP is in TDB? Mm-hmm. Oh, and then we're just going to dereference it?
We don't have to dereference it, right? The address of the marker minus 2 pointers. Minus 1
but
pointer.
that itself is a pointer.
Yeah, that's fine. We're passing
right,
it
the
to
address
right.
of the marker is our theoretical stack pointer minus 2 pointers. Now you have to okay. Yep. Yep.
I think that's a very low chance that this will work, but bang.
Try foo after it. You didn't actually send it. Give it anything.
Oh. Oh, it's plus though, right?
I think you're right. It is plus.
Gold. Oh, I feel like it's close. We're close here. We can find
if echo was only this easy.
Yeah.
This is always the way the show goes, right? We get to inches away and then we solve it in the after party.
Okay, I have one last gasp. Ready for the one last gasp?
I'm ready for it.
That builds. Oh, well, that's not going to build because I'm bad.
Oh, yeah. Sure.
I want this to be 64-bit int.
Yeah, that's another thing libc does, is gives you portability. Initialize the variable sp to silence this warning. You have to mark it volatile? I guess register does that.
There's a warning, right?
Warning is uninitialized when used here.
Okay, we're deleting W error. Always a good sign.
Fantastic.
Didn't work. All right. I give up.
We tried.
We saw it in GDB. We saw it in GDB, which is pretty good. But we couldn't quite find it from inside the C language. Our assembly foo was not quite strong enough to recover the stack pointer.
Well, last time I wrote assembly was a long time ago, and I definitely wrote assembly a little bit in my professional career, but my major source of assembly knowledge actually comes from writing Itanium.
Itanium
assembly in college. And I remember, because my physics professor, because I went to a tiny school that didn't really have much of a CS program, but the physics professor had an Itanium box that he'd gotten. And so we were learning Itanium as our assembly. And then I later met someone, probably on the Chrome team, who'd worked on the Itanium project. But anyways, any last thoughts before we part?
Use libc. Libc's got a lot of good code in there.
There's also a lot of different libcs if you don't like the one that came with your system, because people have sat down and written their own. So anyways, good to see you as always. Wonderful to see all the folks come by. Sorry we didn't get to echo, but hopefully you enjoyed the tour of Linux of sorts.
Oh, great. Glad you enjoyed it.
Yeah, we'll see you all next week.
See you next week.